All right, we're going to be talking today about equations of lines in 3D. So first, let's talk about equations of lines in 2D. The way we usually write them is as a function, which is the same thing as the output, which is, say, 3x plus 4. The interesting thing about this way of writing lines is that the x itself is part of the graph of the line. In 3D, oftentimes the parameter or the independent variable we will use is not part of the graph itself. What I mean by this is, okay, so when x is 0, we have the point 0, 3. So this is part of the line 0, 3. When x is 1, then we have 1 and then 7 and so forth. And when x is negative 1, then we have negative 1, 1, negative 1, 1, and so forth. So those points make form the line that corresponds to this equation. In 3D, we are going to use most of the time a parameter, and the parameter will not be graphed, will not be part of the picture of the line as x is in this case. Having said that, there are some similarities when we write the equation of a line in 3D. In 2D, 3 describes the slope or direction, which is 1 over and 3 up, that is the slope. And 4 is a starting point on the line. The starting point is when the input is 0, and then the output is 4. So we're going to have a similar situation with 3 dimensions. We're going to write the function as typically as r of t. All right, and that's going to have that is going to be written as a vector, which is going to give us a direction t plus an initial a position. So this is going to be an initial position, and initial position, and this is a direction vector. Both are vectors, but as I mentioned in one of the first or in a previous video, a vector could represent a direction or a position depending on the context in which it is used. Yeah. So one thing we will notice is that in this case, t is absent from the picture of the line. So we will have, say, this is r naught, and then we have a direction m, a direction vector m. And so when t is equal to 0, we have this, we start at this point, just like up here, when x is equal to 0, we start at that point. When t is equal to 1, then we are at this point. We should probably have an example to make this a little more clear, but when t is equal to 1, we will be here. However, the 1 is not necessarily involved in the picture. There's not necessarily going to be a 1 in the coordinates of this point. When t is equal to 2, we will have this point, which is 2 of those out here. However, the number 2 may or may not, typically won't be part of the coordinates of the vector. When t is equal to -1, we're going to be back here and so forth. So those are going to be the points on the line. T will be somewhere else. So we think of the parameter t as sitting somewhere else and not being part of the picture. Oftentimes we think of this as time, not necessarily, but it could very well represent time. And we don't visualize time. We know what happens as time goes by with objects, but we don't visualize time. Some people describe it as the fourth dimension, but it's just, we will call it a parameter as, or an independent variable. As t changes, so does the point, just like here, as x changes, so does y. As t changes, so does the point. All right. As an example, we could have so this is going to be our example one, if you will. We will have r of t equals 2, 3, 5 t plus 0, 0, 4. 0, 0, 4. So this vector describes the slope. Well, it's not the slope, the direction in which we are going. And this is an initial value point on the line. So let's do this on a new page. Yeah. So again, example 1, r of t is going to be 2, 3, 5, 2, 3, 5 t plus 0, 0, 4. So in this case, we start out at 0, 0, 4. Yep, 0, 0, 4. Whoops, 4. And then when we add 1, when t is equal to 1, then we add 2, 3, 5 to 0, 0, 4. We're going to end up with 2, 3, 9. So somewhere in there, we're going to have 2, 3, 9. That's when t is equal to 1. And this is the point when t is equal to 0. And so we have this, a line going this way, going through this point. Notice that 1 is not part of the point. In our two-dimensional example, when we have x and y, if you plug in 1 for x, 1 is part of the coordinates of the point. In this case, 1 is not any of the coordinates of the point. Yep. One of the reasons why we want to have a parameter is because in physics, that could be a way to control the velocity at which the point is traveling along the line, the point with coordinates x, y, and z. Oh, before we do that, we change the parameters. Let's change the form of the equation of the line. So this is the equation of the line in a vector form. So this is the vector form of the equation of the line in 3D, but we can have a parametric form. Parametric form. So let's rewrite r of t again, 2, 3, 5 t plus 0, 0, 4 multiply through the t. So we have 2t, 3t, 5t plus 0, 0, 4, which means that when we add those two vectors, we end up with 2t, comma, 3t, and 5t plus 4. Oftentimes, I will write the equation of a line or a curve in space for that matter this way. So this is kind of in between parametric and vector. In my opinion, it is more parametric than anything else. And the reason is because if we break this up into its pieces, x, which is really a function of t, is 2t, y, which is a function of t, is 3t, and z, which is a function of t, is 5t plus 4. So here are our parametric equations. Parametric equations of line. Okay. One of the problems with parametric equations is that there are many, many ways to write a parametric equation or a set of parametric equations for the same exact line, the same graph. Let me give you some examples. Well, the same example, but let me change the line. If you have x equals, I'm going to copy this again, x equals 2t, y equals 3t, and z equals 5t plus 4. The parameter is this t. Each one of those equations is linear, and consequently, the graph we're going to obtain is going to be a straight line. If one of those was not linear, I'm going to come back to that in a moment. If one of those was not linear, then the graph will not be a straight line. But there's a catch to that. There's more to say about that. Okay, so this is the line that starts at 0, 0, 4 and goes in the direction 2, 3, 5. If, however, we change those parameters and we replace them with 2t instead, so we have a new set, x equals 2 times 2t instead, y equals 3 times 2t instead of t, and z equals 5 times 2t plus 4, which in turn will be 4t, 6t, 10t plus 4. This system of parametric equations will describe exactly, identically, the same line. However, the way it is drawn is differently. It will still start at 0, 0, 4. However, this line is going to go faster. When t is equal to 1, so let's compare. When t is equal to 0, we have the point 0, 0, 4. 0, 0, 4. So this is our starting point. When t equals 1, we have the point 2, 3, 9. 2, 3, 9. Compare with this guy. When t is equal to 0, we still have, I don't want to confuse those two, we still have the point 0, 0, 4. But when t is equal to 1, then we have a different point than that one. We have 4, 6, 14. 4, 6, 14. And it isn't that this point does not belong to the line described up here. It is that it takes longer to get to this point. We get to this point when t is equal to 2. So 2 times 2 is 4. There's the 4. 2 times 3 is 6. There's the 6. 2 times 5 is 10 plus 4, 14. So this line will get through this point, but it will take longer. It will take t to be equal to 2, while this line gets there sooner when t is equal to 1. So we have to be careful. The difference is that even though we start with the same point of 0, 0, 4, the vector we're using to travel through the line is going to be longer, 4, 6, 10 versus 2, 3, 5. Yep. So we got to be very, very careful with parametric equations. Let me give you a third variation of the same kind of line. Well, say x equals 2 times sine of t, y equals 3 times sine of t, and z equals 5 sine of t, close the parenthesis, plus 4. Notice that the pattern is very similar to this one. 2 times input, 3 times input, 5 times input plus 4. 2 times input. The input is more complicated. Nonetheless, it is an input, which is repeated down here and down here in the same fashion as up there. This will cause the line to stop. Instead of having a straight line, an infinite line that goes all the way to, let me change what I was going to say, that goes on and on without stopping. This line does stop. So initially it starts out when t is equal to 0. Let me draw a bigger table here. When t is equal to 0, then we have the point 0, 0, 4 as before, 0, 0, 4. When t equals pi over 2, then sine of t achieves the value of 1, and we end up with the same point as up here, 2, 3, 9. Yep, 2, 3, 9. However, when t is equal to pi, well, we all know that the sine of pi is equal to 0, so we go back to 0, 0, 4. When t is equal to 3 pi over 2, well, the sine of 3 pi over 2 will be -1, so now we are at -2, -3, -1, -2, -3, -1. And then when t is equal to pi, rather 2 pi, we go back to 0, 0, 4, 0, 0, 4. So in the two examples that I showed above, we have a line that goes on without boundary. There's no stop to it. It keeps going. Here, however, the line stops. Well, let's have a starting point, which is going to be 0, 0, 4. It stops at 2, 3, 9, 2, 3, 9. So it goes up here, turns around 180 degrees, comes back through the same point. Then it goes down to -2, -3, -1. Turns around 180 degrees, goes back through the same initial point, and it oscillates back and forth between this and this point. Just like the sine function goes up and down, except that there is no width to this. This will run over the same segment of line. So we end up with a segment of line. We got to be careful when we parameterize this way, this segment of line, because we want to make sure we don't run over the line more than once if we don't intend to do that. We're going to be integrating over lines, and if we happen to parameterize a segment of line, we want to make sure we don't run over the same line more than once. We typically don't use sine, but we could use sine to, or cosine for that matter, to represent a segment of line from one endpoint to another endpoint. So this is an interesting example because it is linear without being linear in a way. It is not linear because we have a transcendental function, sine of t, but the output is perfectly straight, a segment of line. You may be thinking, well, that's kind of not quite right because we don't have the same line as the one up here. We could have a line, for instance, if y was equal to 2t cubed, I'm sorry, not y, x. Y equals 3t cubed and z equals 5t t cubed plus 4. Then we have the same exact line that has no stop to it. There's no segment and there's no repetition or coming back to anything. It starts at 0, 0, 4 as the previous one, 0, 0, 4. And then it goes through all the values we had before, except that it goes, once it hits 2, 3, 9, 2, 3, 9, the line is drawn faster and faster and faster, as opposed to the other example, x equals 2t. Let me write it horizontally so I can fit more into the page. Y equals 3t and z equals 5t plus 4. This line has a uniform velocity versus this line. This one has a variable velocity. And by that, what we mean is that the point that is drawn using those equations initially is slowing, it is slow rather, and then it is going faster and faster and faster as we go. So we can change the velocity at which the point is being drawn with a parameter. We can even change the direction, as you saw with the sign. You can manipulate the line in different ways. One more example, say x equals 2t squared, y equals 3t cubed, and squared, and then z equals 5t squared plus 4. All right, a quadratic does not go into negative numbers, and consequently, this line will come from far away, gets to 0, 0, 4, turns around 180 degrees, and goes back into the same path. So it's sort of a parabola that has been squished into a ray, where the point here is 0, 0, 4. There's nothing down here. Again, the line comes down, turns around 180 degrees, and goes away. Yeah, so this is a ray as opposed to a straight line. Yeah. We could reparameterize the line. You just have to be very careful with parametric equations. There's many ways to write the same line. So let's go back to our original example. X equals 2t, y equals 3t, z equals 5t plus 4. So you may be thinking, okay, as long as I know that is the parameter, then I can tell the pattern is 2, 3, 5 for the direction, 0, 0, 4 for the starting point. Not so fast. We can change the parameter in many, many different ways. Not only we can change the parameters so that it is not linear, we can change it so that it is off altogether. Let me show you what I mean by that. Let's do a change of variable. So set S to be this, 5t plus 4, 5t plus 4. So t, in turn, will be S minus 4, all of that divided by 5. So 1/5 of t minus 4/5. Let me make sure I'm doing this correctly. So I'll subtract this would be S. Subtract the 4 from both sides. So we end up with S minus 4, and then divide by 5. So let me write it a little more neatly. 1 over 5 S minus 4 over S, over 5. Okay, so we can rewrite this line as follows. X will be 2 times not t, well, t, but written this way as 1/5 s minus 4/5 multiplied by 2, and we end up with 2/5 s minus 8/5. Y would be 3 times this, so 3 over 5s minus 12 over 5, and z would be s itself. So we can rename s. Let me do it over here. Rename s to t. So instead of calling it s, we can rename it and call it t. So x becomes 2/5 t minus 8 over 5. That's a 5. Y equals 3 over 5 t minus 12 over 5, and z is equal to s. Let me rewrite this. Oh, just t rather, t. That's a little bit too messy. Let's rewrite this. So our original parametric equations were, let's just make sure, x equals 2t, y equals 3t, z equals 5t plus 4. By renaming this, by changing this into s and renaming it back to t, we have a new set of equations. X is 2 over 5 t minus 8 over 5. Y would be 3 over 5 t minus 12 over 5. And z would be just t. It turns out that even though the pattern doesn't appear initially to be the same, we have 2, 3, 5. Well, it is the same if you pay close attention, because if you multiply, if you realize that this is actually 1/5 multiplied by 2, you do see the 2 and the 3 and the 5. So the direction is there, it's just written differently, and it has a different velocity to it as well. It is not obvious that those are the same lines, at least not initially. The starting point of this line is 0, 0, 4, as it has always been, because that's what happens. That's the point we obtain when t is equal to 0. However, this line starts somewhere else. It starts out at negative 8 over 5, negative 12 over 5, comma 0. Yep. So it starts somewhere else, but it has the same direction. However, the direction vector doesn't have the same magnitude. The direction vector, so this is the starting point, start here, and this starts, and by start, what we mean is when t is equal to 0, the direction is 2, 3, 5. Let's call it m, even though it's not the slope, it's the direction. So I'm putting quotation marks. So the slope in quotation marks, because we don't really have a slope. The direction is a better way to describe this. For this parameters is, or parametric equations is 2, 3, 5, 2, 3, 5. While here, the direction would be 2, 5, 2 over 5, comma, 3 over 5, comma, 1. And those two vectors are the same direction. This one is longer than this one. Yeah, this one, I believe, is longer 5 times as much as this one. Yeah. So this line will be the same line. It will go through the same points as that one. it will start when t is equal to 0 in different places. It will go in the same direction, but this line is going to go slower. So it will take 5 units of t to achieve the same as 1 unit of t here. The other way to put it is that this one is slower by a factor of 1/5. All right. So t, the parameter t, can make things nicer, but it can complicate things as well. That's why we try to keep t as simple as possible. The parameter should stay as simple as possible. You can complicate things if you want to. Try not to, unless you have to. Occasionally, we do have to. Yeah, it is good to know that we can change things and make things more complicated, because there are times when we may need to do that. An analogy that I have for that is, what is better, to have $5 bills, $1 bills, bunch of quarters? It depends on your application. Sometimes you want a change of singles and quarters if you're using a vending machine. Sometimes you want bigger bills. It varies depending on our application. So the same thing happens here. We can have different ways to parameterize lines depending on the application. Now, if you are not concerned, or if one is not concerned about the parameterization, we can go back to regular equations. Oh, before I continue, let me just say one more thing about this example. This example, when one of the parameters is equal to one of the variables, we can say that in this example, z is the parameter. So in this example, the line sort of goes back to our first line in 2 dimensions. Yeah. Remember at the beginning today, we said that x was part of the coordinates. So if x is 1, there's 1 in the coordinate. When x is 0, there it is. When x is -1, the -1 is part of the coordinates of the point. If we have this situation where t is one of the coordinates, is equal to one of the coordinates, then t will show up. Rather than the coordinate, well, yeah, the t, which is the same as that coordinate, will show up in each one of the points. If t is equal to 1, there is the 1. If t is equal to 2, well, we're going to end up with a point where this value will be 2. So another way to say that is that we have parameterized this line so that z is the parameter. It doesn't have to happen, but you could do that. Yep. Yep. All right. Let's talk about symmetric equations. So next, symmetric equations. And they're called equations plural because we need more than one equation to represent a line. A line in 2 dimensions can be represented with a single equation. There it is. We'll do that. But in 3 dimensions, we need 2 equations. Yeah, one that well, actually, yeah, 2 equations will do. We can have some redundancy and have up to, let's see, 1, 2, 3. I'll show you. All right, let's go back to our original equations, parametric equations. 2t, that was x, 3t for y, and z, 5t plus 4. If we solve this equation for t, then t will be x over 2. If we solve this equation for t, then t will be y over 3. And if we solve that equation for t, t will be z minus 4 divided by 5. Z minus 4 divided by 5. Well, this is the same t across the equations, just like back here, we use the same t value to obtain perhaps different x values. So those are the same, and we can write them together as one longer equation. So x equals 2, which is t, is equal to y equals 3, which in turn is equal to z minus 4, divide that by 5. And that is what we call symmetric equations for the line, the ones I boxed. So that's why I mentioned that there's actually 3 equations, although 2 equations are sufficient. So those 2 are equal. Also, those 2 are equal. But then by transitivity, those 2 are equal. And that gives us a relationship between x and y. So if we do cross product, every 3 x's is equal to 2 y's. And this gives us a relationship between y and z in turn. So if you fix x, you can figure out y. If you figure out y, you can find z. But it works in every one direction. If you start with z, then you can find x, and you can find y, and so forth. So the beauty of this, there's advantages and disadvantages of this symmetric equations, is that there's no parameter. The parameter is gone. You can set x to be any number you want. Well, you can set x to be 1. So 1/2 is equal to y over 3, and then you got to figure out what y should be. So there's no parameter involved in this. However, when we are dealing with straight lines and curves in space, many of the operations, many of the computations we perform are way better if we use a parameter than if we use symmetric equations. When you have symmetric equations, the denominators, if we have coefficients of 1, of course, on the variables, then we never write them down, but I'm emphasizing that we have a coefficient of 1 for each one of those variables. Then the denominators describe the direction. So the direction of the line is 2, 3, 5. And then whatever we subtract from the y, rather from the variables, describe the starting point. So 0, 0, 4 is where we start, and the direction is 2, 3, 5. That makes it simple to figure out how to write symmetric equations of a straight line. There's one more thing we need to talk about, and that is the segment between 2 points. Yeah, we need to describe a segment between 2 points. Yeah, we definitely need to be able to do that. So let's say you start out at A, B, C, and then you want to end up at L, M, N. We want to be able to parameterize to travel from this point to this point. Yep. Yep. So the standard way of doing this, we can do this in many ways. For instance, you can, well, let's go back to those different ways in a moment, but the standard way to do this is to come up with a function that has A, B, C to start with, A, B, C. We want typically t to go from 0 to 1. So when t is equal to 0, we want to start out with ABC. So we put 1 minus t. So that's where we start. But then when t reaches 1, we want to be off of this point completely and completely on this point. So we're going to add t times L M N. There we go. So this equation will take us from ABC to LMN as t goes from 0 to 1. Yeah. We want to be able to do that. And this is one of the simplest ways to go about it. Let's see. So R of t will be, if we distribute the 1 over multiply with a 1, we end up with ABC minus t ABC plus t LMN, and that is going to be, let's see, A minus t, we can factor out the t, and then we have, well, let's factor out t plus t rather. So we will have L minus A, that is the first coordinate, B plus t, M minus A, and then C plus T and minus C. I forgot if I said B here, that should be B. All right. Notice that up here, the vector that goes from ABC to LMN has coordinates L minus A, M minus B, and N minus C. Yeah. So those are the coordinates here. Some people will say, hey, you forgot to put the commas. In my personal opinion, if it is clear that we are dealing with 3 dimensions, and we are dealing with 3 dimensions, it is established up here. And this is my personal opinion only, though. I'm not asking you to necessarily do this. If it is clear, and there are only 3 items in between the parentheses, then I don't know. Let's put the commas. I can see. Within reason, we can be a little bit free, but not. But we should be more proper in this case. So there it is. We could use perhaps sign to do this. Yeah, so let me go back to this. So we started with the vector A, B, C. We're going in the direction L minus A, M minus B, N minus C, and we are using the parameter T to achieve that, to go from A, B, C to L, M, N, because by the time T is equal to 1, we are also subtracting A, B, and C. Can we do this with a different parameter? Instead of T, can we use a different parameter? Absolutely. So if you want to go from, again, A, B, C to L, M, N, we can start out with A, B, C plus a parameter, a quantity that will go from 0 to 1, and then L minus A, comma, M minus B, comma, N minus C. And then the parameter we'll use could be sine of T instead of T. that will achieve exactly the same thing, although the velocity at which we go from ABC to LMN is going to vary. And also the parameter has to be established so that we go in one direction only once. So we go from 0 to pi over 2. So this will do the same thing. This is a segment that goes from ABC to LMN once in that direction. However, we are making this parameterization more complicated than it has to be. Sine of t can be more complicated than what we need it to be. All right, with that, we will stop equations of the line.